Hello, everyone. I'm Kaihui Gao from Tsinghua University. I'm proud to have the opportunity to present our paper, Buffer-based end-to-end request event monitoring in the cloud. This is a joint work with my colleagues from Tsinghua University and Alibaba Group. Modern cloud applications are embracing cloud native by reconstructing monolithic applications into microservices. Remote procedural calls, or RPCs, are widely used for communication between microservices and have become a fundamental component in clouds. There are 440 million RPCs per hour per storage cluster in Alibaba Cloud. Due to the wide use of RPC, the latency of RPC is increasingly crucial for application performance. Consider an app with 5 sequential RPCs. If RPC latency is 30 milliseconds, the total request latency is 150 milliseconds, which can deliver a satisfactory user experience. However, if RPC latency is 200 milliseconds, the total latency reaches 1 second, which brings poor user experience. Unfortunately, RPC latency anomalies is widespread in production cloud. Data shows that the latency of 44,000 RPCs exceeded 100 milliseconds per hour per cluster. However, RPC latency anomaly, or RLA, is extremely difficult to diagnose. This is because an RPC goes through multiple layers, including network stacks, NICs, network links, and switches. All layers may expose anomalies, while different layers are managed by different teams in the cloud. Existing tools are designed to diagnose RLA in one layer, not all layers. For example, application performance tracing tools monitor end-to-end RPC latency, but has no detailed insight in lower layers. Meanwhile, many tools focus only on detecting problems in the stack or physical network. So, existing tools have incomplete visibility across the RPC lifecycle. What if we combine tools at different layers? For example, the application detects latency anomaly for RPC2 and queries networks for any ideas. Networks don't have RPC semantics and requires flow information. When the application provides IP and timestamp, the network say, sorry, I see a burst, but I'm not sure if the RPC is affected. The inconsistent semantics in different layers make it impossible to correlate monitors with each other. As a result, it often takes hours to days for operators from server, networker, or NIC teams to come to a conclusion. So why is RLA diagnosis so difficult? The application and the network stack in software are white box, while traditional NIC and switch are black box. Operators in different layers have to monitor each layer with heterogeneous model and distinct semantics. So, is there any opportunity for us? Our answer is that with modern programmable NIC and switch being deployed, networks are becoming white box, making it possible to uniformly model all layers and enforce consistent semantics. The next question is, what is the right uniform model for RLA locating? We further analyze each layer and abstract modules in each layer into 2 types, including logics that process data and buffers that ameliorate speed mismatch between upstream and downstream logics. Different layers process data in different ways and may encounter diversified and complex problems. For example, in network stack, problems like code bug and CPU contention may happen. While in the network, issues like long configuration or link failure may occur. It is unlikely that we build a unified model for logics in different layers. On the other hand, buffers are often homogeneous in all layers, and they experience similar events like overflow or out of order. Moreover, events in buffer can indicate the location of RLA. For instance, buffer overflow often indicates slow downstream logic. So it is highly intuitive to choose buffer for allocating. Based on the intuition, we analyzed almost 500 production RLA tickets from Alibaba Cloud and summarized the root costs and the locations in this figure. We observed that more than 90% of RLAs expose anomalies in buffers. So we propose a buffer chain abstraction to uniformly model all layers. We can simply monitor the appearance of buffer events for our locating. Based on this model, we propose BufScope, which diagnoses RLAs based on buffers. BufScope is designed to achieve 3 goals, including complete visibility at all layers, consistent RPC-level semantics, and low CPU and performance overhead. Achieving above 3 goals is challenging. First, different types of buffers have different abnormal events. For example, lossy buffers may drop data, while lossless buffers post packets, and the TCP buffers maintain packet order and may delay packets. So defining events for various buffers is not easy. Second, buffer events in all layers should be finally correlated to RPC. However, such information is deeply hidden in packet payload, making it uneasy for NIC and switch to pass out RPC IDs. Finally, adding complex operations in software may introduce CPU overhead and affect application performance. Next, I will present our solutions in BufScope. To understand the diversity of buffer events, let's traverse the buffer chain with an unlucky RPC message. When it enters the network stack, the message may be congested. Next, the NIC can be configured with multiple priorities. The message is delayed due to priority contention. Then, in a lossless network, switch 1 is paused due to congestion in switch 2. When it reaches the destination NIC, packet drop may happen. Finally, it enters the reserved TCP buffer, and the message still has to wait for retransmission of out-of-order packets. So far, we have observed 5 types of buffer events caused by 3 types of buffer properties, including priority awareness, in-queue features, and order sensitivity. In addition, all buffers may encounter congestion events. So when deciding which events one buffer may encounter, we classify the buffer according to the 3 properties and identify corresponding events. Next, let's take 2 types of buffers as examples. First example is a switch buffer with multiple priority queues in lossy network. It is priority aware, lossy, and order insensitive. So it may encounter priority contention, drop, and congestion events. Second example is TCP receive buffer. It is priority unaware, lossless, and order sensitive. So it may encounter post, out of order, and congestion events. Next, our goal is to use RPC ID to correlate events in all layers, including NIC and switch. Originally, the application layer delivers a stream of RPC messages to the network stack. At this time, when a buffer event happens, we can easily identify the affected RPC. However, Then the RPC stream are encapsulated in packets for network transmission, and RPC IDs are hidden in packet payload. Then one packet may carry partial RPC data without ID, and the location of the subsequent RPC becomes unpredictable. These two situations make it difficult for NIC and switch to obtain RPC IDs from packet. To address this challenge, we propose per packet RPC-level semantic injection. For the packet X, the ID of RPC1 can be easily obtained. The ID of RPC2 can be derived by taking the length of RPC1 as offset. Then we record the ID and the remaining size of RPC2. For the next packet, due to the lack of RPC ID2, we first insert the ID after the header. Then, for indexing to the header of RPC3, we insert the remaining size of RPC2 after the ID. By adding only 10 bytes in some packets, we make it easy for programmable NIC and switch to obtain RPC semantics. Finally, the straightforward location to perform the semantic operations is the network stack, where RPCs are encapsulated into packets, or vice versa. However, we have to perform per-packet processing, which brings large CPU overhead. Besides, event reporting in software also consumes CPU. We leverage several optimization techniques in the implementation to reduce CPU overhead. For semantic injection and recovery, we offload the operations to semantic hardware. For event reporting, we embed one agent in each layer and perform zigzag encoding and batched reporting to compress the bandwidth of events. Next, we present two real cases that happened in Alibaba cloud storage system to show the effectiveness of BufScope. A tenant encountered RLA and provide RPC ID and timestamp to the operator. BufScope comes to help by retrospecting events in all layers. The stack seems normal. Both the NIC and the network expose congestion problems. Data shows that the NIC congestion is more severe and close to tenant experience. Finally, with BufScope, the operator quickly diagnosed the root cause as a pooling harm. Without BufScope, both the server and the network teams feel responsible, and figuring out who is primarily responsible can be a time-consuming task, which took 1 week in this case. The second case is caused by priority contention in the receiver NIC. RPC2 encountered latency anomaly. BufScope detects priority contention in the receiver NIC, where RPC2 is delayed by RPC1. Such indicative clues quickly reveal a wrong priority configuration of application 1, which is a bug in a version update. Without BufScope, the operators first naturally check the logics of application 2, and finally find the bug in application 1, which took 2 days in reality. Finally, we evaluate the event coverage and CPU overhead of BufScope on a spread presented in this figure. We compare BufScope with the combination of state-of-the-art monitoring tools. We implement BufScope over 2 RPC frameworks, including the open source Finagle and Alibaba storage. We use trees from literature for evaluation. Evaluation results show that BufScope can fully detect 5 types of buffer events. Moreover, BufScope only decreased the application QPS by 1% compared with the original application without any monitoring. In conclusion, we have proposed BufScope to diagnose RLAs based on buffers. BufScope is constructed based on a buffer chain model. And we propose 3 key designs, including buffer classification, semantic injection, and semantic offloading. For each RLA, BufScope can clearly quantify the responsibilities of each layer and boost RLA locating from days to minutes. Thank you for your listening, and I'm happy to take questions.